Homework 7, problem 3, find the gyromagnetic ratio for a spinning charged sphere, and then use the angular momentum for the intrinsic angular momentum for an electron, so an electron spin. Find what the magnetic moment for an electron, for such a classical electron, should be. Now, the way I would like to do this, right, is I would like to go ahead and break up my sphere, so I'm going to make a diagram here. This ID is my sphere. I'm going to break it up into a bunch of little donuts. Like that. And so each donut is going to curve around, but I'm going to break it up into a bunch of little donuts, and I'm going to make this the R direction and this the Z direction. And I'm going to say that my gyromagnetic ratio is M over L. I'm going to call that the gyromagnetic ratio, little g. I'm going to say the gyromagnetic ratio for a sphere is going to be equal to the integral of gyromagnetic ratios for donuts. Donuts for the function of R and Z. dr dz over a half circle. So that's the integral that I'm going to be looking at. And so now I need the gyromagnetic ratio for a donut. Luckily, that was the solution for problem 2. And one of the things we found is it was independent of R. All it depended on is the mass that was in there and the charge that was in there. If we have some uniformly charged sphere so that the charge doesn't change as a function of radius, and mass doesn't change as a function of radius, or that they do change, that they change uniformly such that charge and mass are related, then the gyromagnetic ratio for a sphere is also going to be Q over 2m, because we just integrate over it. This would be, the Q for each little donut would be the Q divided by whatever the area is. When you integrate over the area, you're going to cancel those areas out. So the gyromagnetic ratio for the sphere is going to be Q over 2m. So that's the first part. Second, given angular momentum for an electron, find the magnetic moment. So magnetic moment, of course, is then going to be this gyromagnetic ratio, which is Q over 2m times the angular momentum. Plugging in values for an electron, we get the charge of the electron, E, over 2 mass of the electron, times the spin, which is h bar over 2 in the z direction, right? Okay. So just taking this expression here, rewriting it, we have that this is E h bar over 4 me. Now we can relate this. This is, if we do, we can relate this to something called the Bohr magneton. This is 1/2 of the Bohr magneton, where the Bohr magneton takes on the value E h bar over 2 me. And the Bohr magneton was defined as the magnetic moment for a electron in an orbital. And so Bohr did this model of the atom where the electrons existed in these quantized orbital. If you treat the electron as a particle going around this orbital, this is a magnetic moment you would find for that case. Okay, so that is the solution to problem 3.